Welcome back, everybody. This is our video solution to problem 4 from Quiz 8, Fall 2023, Math 307, Linear Algebra at Cal State Fullerton. In this problem, we have an inner product space V over the complex numbers, and we choose some element V in the vector space V and some complex number Z, and we want to prove what is actually just a very, very standard fact about the norm in an inner product space, which is that if you take the norm of a scalar product, right? So here we have a scalar z times the vector v, then I can pull the z out at the cost of taking the length of z, magnitude of z, norm of z, whatever you want to call it for the complex numbers. So we're going to prove this, and it's going to be a pretty easy consequence of the axioms of an inner product space. So first, let's go to the definition. If I take the norm of zv, this is equal to the square root of the inner product of zv with itself. All right, well, it's going to be, I don't know, maybe inconvenient having to carry this square root around. So if I square the left-hand side, I can just make the square root go away. All right, so that's not too bad. Now, because I have first argument linearity in an inner product, that means I can pull this z out of the front. So this would be the same thing as z times v comma zv. All right, now I would like to pull the z out of the second component, but I don't quite have second argument homogeneity. It's almost second argument homogeneity. It's actually second argument conjugate homogeneity. I can pull this z out, but I have to give it a complex conjugate. So this is equal to z bar vv. Okay? And just as an aside, let's kind of remind ourselves why this is. So one of the axioms for being an inner product space is that I can take v zv here and spin it around. Right? Make this zv comma v. But if I do so, it gets a complex conjugate. But now I do have a z, right, scalar in the first component, so I can pull it out. But this complex conjugate still reigns over it, right? So this would be the same thing as z bar times v bar. And then, of course, I can switch the v and the v around, and that'll get rid of the conjugate. Of course, switching v and v around doesn't do anything. So this will equal z bar times vv. So this shows why I really can pull the z out of the second component, but it's going to pick up this complex conjugate. Okay, but now z times z bar and then the inner product of v with itself. Well, the inner product of v with itself, this is the square of the magnitude or norm of v. And what about this z bar? So, well, what this is going to equal is the length of z squared. And let's see why that is. So if I have z equal to a plus bi, then z bar will equal a minus bi. And if I multiply them together, well, this is now a plus bi and a minus bi. Ooh, difference of squares. This is a squared minus bi squared. But bi squared, well, let's see, the I squared is -1, so this becomes a squared plus b squared. And a squared plus b squared is precisely how we defined the square of the length of z, right? If we go back to the complex plane, maybe I have some a plus bi over here. And I say, oh, okay, what's that length? Well, I come down here, and this is a, so this has length like the absolute value of a. And what's the height? Right? What is this height here? Well, this is bi, so the height here is the absolute value of b. Actually, it equals b if we're in the second quadrant, but that's fine. And now by the Pythagorean theorem, I know that the square of a plus the square of b will be the square of this length. And that's where this formula comes from. Right? There's the length of my z. Okay, and so we now just need to take the square root at the end, and we'll get that the magnitude of zv is equal to the length of z times the magnitude or norm of v. And that's what we wanted to prove. So there we go. All right, everybody, we will see you next time.